Previously, we mentioned that in nanotechnology, in bottom-up nanotechnology, we exploit the degree of freedom that molecules and atoms have in the fluid phase. Today, we look at the fluid phase and we choose to focus right now on one of the two models for fluid. We mentioned before the discrete model and the continuum model. That's what we are talking now about. Before we go into the math, we need to focus on what makes fluid unique. What, for our concern here, is the big difference between fluid and solid. And the difference is here, cross-migration of momentum. When you have solid, and you have a force applied on some piece of matter, then this matter moves in the direction of the force. It doesn't suddenly pop up or sideways. The force has an impact in the direction in which it applies. But in fluids, because of the degree of freedom, that is the essence of fluids, we have cross-migration of momentum. And let's illustrate. Here there is a little particle or a molecule traveling in the x direction in a particular speed. It has a mass, it has a velocity, mv means it has momentum. Only in the x direction. Now along comes another molecule here that travels this way. It has this vector represent the momentum in the minus y direction, and a here is the projection of its momentum on the x direction. Boom, there is a collision. What happened after the collision? Some of the momentum from this molecule was imparted to this one. So now it goes with this momentum. And the projection of this momentum on the x direction is b. So what is the net result? Because of this interaction, the previous level of momentum, it was A, is now B. And the B minus A was added, not here, but at a higher level, at a different y direction. So we have here a mechanism that x directed momentum migrated to the y direction. Same way it migrates to the z direction. And the same way y momentum migrates to the x and z to x and y. That's why, as we will see, we need this tool of tensor calculus to express this complexity. Here are the details. Balance of momentum within a bulk of fluid in the continuum model. We simply define a small unit of volume within this bulk and ask ourselves, how will we express Newton's law over this volume? Newton taught us that F equals ma, or m dv to dt. mv is the momentum, mass times the velocity. Therefore, m dv, assuming mass is fixed, m dv to dt is the rate of change of momentum equal the force applied on whatever the place is where momentum is changed. So this place for us, using Cartesian coordinates, is a cube like this, which has, it's a position x, y, z, and it has dimension delta x, delta y, and delta z. And we ask ourselves, how will the balance look like? What will be the accounting equation for momentum? And it's very simple. This translates to the rate of accumulation of momentum here equals the total number of forces applied on this area times, or plus the net flow of momentum, because this volume is not surrounded by walls, but is an imaginary cube, and fluid goes through each of those 6 faces. So let's start first with the net flow. Net flow, we have, first of all, when we are looking at one axis, x, we have here fluid that has a velocity vx here flowing through this face, and then some fluid flowing out of the counterface here, which is not drawn. So what we need to do is simply say that the net flow is the difference between what comes in and what leaves. Now, what is the amount that comes in? The amount that comes in a unit of time, because we're talking about the rate, is this green marked volume, which has the dimension of dy and dz, and for the x-axis it has the vx, because that is the amount of matter that flows into this reference cube in 1 unit of time. So the total volume is Vx times dy to dz. If we multiply it by the specific gravity, we get the total mass. We multiply it then we have to multiply it again by Vx again to get the total momentum that is flowing in, and a similar expression for what flows out. Now, what's interesting is that the x momentum also enters through all the other faces. Here, this depicts the x-axis and the y-axis. We have here a bulk that has a velocity vx, component of velocity vx. And this entire bulk within 1 unit of time, let's say 1 second, enters through the face here. And now all this is found here. How much is this? Again, the same logic as here, because this bulk flows here with velocity vy, then the volume here is vy times the cross-section here. What's the cross-section? dx times dz. And all this is multiplied by vx, because we account not for mass, we account for momentum. So that's the mass, specific gravity, times the volume. That's the velocity. So that is the rate in which momentum enters through a cross axis. The Vx momentum enters through the y-axis. same expression through the z. And again, what enters through the y direction then has to be subtracted by what goes out from the opposite face. And we do the same for x vis-a-vis the z direction. And then we do the whole thing again, where instead of x, we analyze what happens to y. Completely symmetric. And then we analyze what happens to z. It piles up to a few expressions, but it's very simple because it is symmetric and it applies again and again the same thing with change of subscript. Now, all this is how momentum goes on a macro level. But as we know from the description of, or the definition of the essence of fluid, that we have the momentum that transfers on the molecular level, like we have seen before. This is expressed through an equation that says that the rate in which the velocity in direction x climbs up to a direction y is proportional to the force that is causing this. And mu is the viscosity or the coefficient of proportionality. So this expression represents the transfer of momentum unique to fluid, molecular level. And here again, this is the rate in which, on a molecular basis, the momentum goes through this phase. We have to subtract it from what goes from the other phase, and then we apply it to all the 6 phases. This applies to all the combination, yx, yz, zy, xx, same thing. Also through all 6 directions. Again, more and more expressions that pile up. But they are symmetric. So we can get our mind wrapped around them. What's missing? The forces. 2 types of forces. This volume has a pressure, let's say in the x direction, and a pressure at the x plus delta x, which is the other face of this volume. So the net is the difference between those 2 pressures because they apply on the same cross-sectional area, which in this case it's dy times dz. And we have to add to this non-surface forces, which can be electromagnetic or gravity. Let's put electromagnetic out of the equation right now and just account for gravity. So the direction of the g of gravity in the direction of x, because we don't know x where it stands relative to the pull of the Earth. So that's why we identify gx and the gy and gz times the specific gravity times the volume, which is dx, dy, dz. So we have here all the components. We can enter all these components into this equation, and there you have it. The expression of the balance of momentum. Finally, we take all the elements that we accounted for that have an impact on the balance of momentum within this control unit, this volume, this cube, which is our control unit. We put them together and we arrange them according to Newton's law. So, the balance is as such. The rate of change of momentum within this control unit equals to the net input of momentum because of flow of the fluid because of the mechanism of cross-directional migration of momentum, which we have seen before, plus the sum total of forces on the same control unit. So what do we get here? This is the expression of the rate of change of momentum only in the x direction. All this is just the accounting for the x direction. We have a similar equation for the y direction and the z direction, but that's only for the x direction. What do we have here? The total mass, which is specific gravity times the volume. That's the mass. You multiply it by the velocity in the x direction. What do you get? The momentum. You derive it with respect to time. What do you get? Change with respect to time. Rate of change. So that is the rate of change of momentum within the control unit. Is expressed by, first of all, the convection. The momentum that comes in the control unit, because the walls are not walls, they are just imaginary boundaries, because of the flow, a bulk flow of fluid in and out. And this is the expression. What do we have here? We have here a summation that uses a dummy variable, I. I simply is rotating between the values of x, y, and z. We write it this way because the expression is the same regardless of the value of I. And we have, this is the summation of the convection, which, just to recall what we have done a minute ago, what do we have here, for example, in accounting for the migration of the bulk that flows through the y direction? But it's fluid that we account for in its x direction momentum. It flows up because it also has a vy, a velocity in the y direction. But we account only for the momentum in the x direction. So what do we have here? We have here the total mass, which is the specific gravity, times the cross-sectional area where it flows, times the Vy, which is represents the total mass that flows into this particular phase in a unit of time. That's what velocity is. It's the distance over a unit of time. So that is the volume, Vy times dx times dz. And we do account for the net input. So we take the input at a y plus dy minus the input at point y. Now this we can now change a little bit by multiplying this expression by dy and dividing it by dy. And therefore we get here this expression of the derivative of this relative to y, and here we have the dx, dy, dz. And therefore we can take all the dx, dy, dz outside of this parenthesis, and we see for a moment how it works here. But it's all out. And when you summarize it over all directions, all 6 faces, that's what you get. That's the convection. Now we have here the cross-migration, this viscous, this molecular transfer of momentum, which we have seen is relative to the stress times the total area where it goes through. And when you do the math similar to this, you get the same similarity of dx, dy, dz multiplied over this entire expression. Same thing for the last element, which is the forces. The forces are the change of pressure between one wall, imaginary wall, at x, and the pressure at x plus delta x. That is the net pressure felt on this volume, plus the volume force, which in this case we only account for gravity, which is always there. We assume that no electromagnetic force is applied, so that's the equation. And we can see that this volume can easily be eliminated. We get it a little bit more simple, and that's only the equation in the x direction. We have the same thing for the y direction and the z direction. And here is how we write it in summary. This is the same equation in a more concise form. It reflects the total momentum in all directions. So we took the convoluted, massive equations that we had before for the x, the y, and the z directions, and we managed to apply a convention of symbolism that gives us the possibility to write it in a more manageable way. But that is exactly what we had before in details. That's the rate of accumulation, that's the of momentum, total momentum, that is the total impact of convection, of bulk flow of fluid, that's the total impact of the viscosity, of the cross migration of momentum, that is the impact of surface forces on all directions, and that is the impact of gravity. Same equation, more concise form, that's the balance of momentum over a small unit of volume, expressed in Cartesian coordinates. One of the advantages of tensor calculus is that the expressions are the same in all systems of coordinates. And it's easy to transform from one to the other. With this, we have the tools to integrate over a large number of control volumes and then propagate from the present status what will happen a second later, a minute later, etc. We can model the behavior of fluid. Now, to do it right, we need to use all the tools that we have. What are other tools that we have still need to be discussed? One is we know the law of conservation of material. So we know that for this particular control volume, total amount that comes in minus what comes out equals what accumulates. Because where will the fluid go? The balance of material, conservation of material. We also have the law of conservation of energy, which also applies. We haven't touched energy here, but a fluid has the thermal energy, it has the velocity, kinetic energy, and has the potential energy because of height. All this needs to be accounted. Coming next.